let's talk about motion. In the book, and I want you to go ahead and read chapter 3. It's not long, probably take you no more than half an hour. Not right now, but why don't you, at your earliest convenience, kind of read through chapter 3. It talks about, and the title of the chapter is Describing Motion, and it's sort of an introduction to kinematics, kinematics is the study of motion. It's our way of being very detailed in our description of motion. Motion obviously plays a huge part in physics, and so in order for us to be able to advance to more interesting and bigger topics, like maybe forces, right? That's kind of one of the first big topics that we'll cancel or that we'll tackle will be talking about how forces produce motion. In order to even start to begin that process, we need to be able to understand how to talk about motion with a common vocabulary, common definitions, so we can be very precise and mathematical in our description of motion. Okay? So they talk about in here, and I'm not going to spend much time on really the first section. They talk about picturing motion, and this is, I get what they're doing here. This is fine. We will abandon this pretty quickly for some more sophisticated ways to look at motion, but this is a great starting place. So the tools that they describe to picture motion are really pretty simple. They use a video camera and maybe a stopwatch. And they have an example. If you look at the top of page 45, it just shows successive frames of a movie of a woman running across a gym. Okay? That describes the motion in a sense, doesn't it? And it's a good way to think about motion in physics is as though we're talking about frames in a movie, and if you run all those frames together, it describes the actual motion itself, right? So, but we want to periodically be able to freeze the motion in one frame and talk about the motion at that particular instant, right? Now, what do you notice if you look at that picture, those string of pictures, the frames in the movie, what do you notice about the background? It's the same. Okay, that's key. That's really important. In order for us to be able to talk about motion in a meaningful way, we have to be able to define some reference frame against which we can measure the motion. So in this case, the camera is measuring the motion relative to the stationary gym, right? Make sense? Okay, and that's fine to do. That's fine to do. What do we typically in our everyday lives, what's our reference point for all of our motion? Well, maybe you might think of it that way, but I can be even broader than that. What is always there for us to act as a reference point for our motion? The floor, aka maybe even the earth, right? The floor is stationary, it's glued to the earth somehow, whether it's concrete or who knows how they've done it. But anyway, we're glued to the earth, and the earth is our constant reference frame. Is it a perfect reference frame? No, it's not. We'll point out some deficiencies. For one thing, the surface of the earth, is it perfectly stationary? No, it does move a little bit, right? The tectonic plates move, and so we don't really account for that motion, but it's there. I mean, if we want to be really precise about it. There's some squishing and washing around and flexing of the surface of the earth. Tidally, the earth changes. Did you know that, I can't remember it's been a while since I've taught physics, but I can't remember what the exact number is, but you've all seen the tides at the ocean, right? You can go places, at low tide, the ocean's way out there. At high tide, it's much further in. There are some places, like there's a place in Alaska, where the tides are just enormous, like they average like 30-foot tides. It's just huge. What causes that? Well, we'll talk about that later. It has to do with the moon, right? The moon pulling on the earth, and it's pulling the water, but it also flexes the land. The land actually moves by a certain number of inches. Also, the earth literally flexes as the moon revolves around it. But it's a pretty good reference frame, isn't it? If we're driving down the road in our car and we say that we're going 65 miles an hour, well, what's that 65 miles an hour measured relative to? The road, sure, right? Measured relative to the road, aka the earth. We could just as easily say, though, if you got your cruise control on and you're traveling down the road in a straight line, say you're going down the gorge, let's say, we could just as easily say, well, let's us be the reference frame, and the Earth is whizzing by us, and it kind of looks that way, and it's true. That's okay. It's not as common, but it also works. We could take our position in the car as being the stationary reference frame, and the Earth is moving by us. You could maybe even get out of a ticket using some combination like that. Maybe you could even say if the officer, you're driving down the road in the gorge and 65 is the speed limit, but you accidentally kind of lose track and you're going 75 and the officer pulls you over, well, you could potentially even say something like, that sign wasn't that specific. The sign just says 65 miles an hour. It doesn't say 65 miles an hour with respect to something in particular. Maybe you took that to mean 65 miles an hour with respect to the car you were passing. So I don't know if you're going to get very far with that argument, but it's important that we measure the motion relative to something, right? Okay, so these diagrams are a little bit helpful with that. You'll do some reading, and it'll kind of walk you through. It's kind of good qualitative understanding of how we can represent motion. I'm not going to spend a lot of time on that. One thing I will say though, they talk about the particle model, and that's kind of useful. If we're going to represent the motion between two objects, like let's say our car is car would work fine. If we're measuring the motion of our car relative to, let's say, some buildings that we're passing or something, do we need to be very artistic in drawing that? Do we need to actually draw a car and a building? It might be fun to do, and I'll try my hand at it this year a little bit, which you'll find humorous, I'm sure. But we don't really need to represent the car as being a car, because the internal motions of the car in that case are not important. The car is not spinning around, hopefully. It's just traveling down the road. The tires moving really are irrelevant to our discussion, right? The building is just sitting there in place, and so it might be more useful for us even to describe the car as being just a point and the building is a point. And so keep that in mind. We don't have to be so artistic with physics. If we're trying to just make a point about motion, maybe we just say this. Here's the path of the car. Let's say the car is moving from there to there, so we can treat it as a particle. And if there's a tall building that we pass by and there's a person standing on top of the building, maybe the person is there, right? That makes sense? I can just draw these points, and that's fine. That's later on, if we need to take into account the more complex internal motions of an object, then maybe we can't do that anymore. But usually, we aren't doing that. Usually we're talking about an object as a whole, okay? All right, so now let's jump into motion. If we want to talk about motion, we have to keep track of a couple key pieces here. We already talked about how we need a reference frame, right? Typically we talk about that. If we want to be very mathematical about our reference frame, we're going to describe it as a coordinate system, okay? And that sounds familiar. We talk about coordinate systems in math a lot. Physics is as mathematical as we can make it. The more mathematical we can make our description of the world, the easier it is to make predictions and to discuss it and know exactly that we're talking about the same thing. So we need a coordinate system. Reference frame typically means we want coordinate system so we can attach numbers to our motion. If we are talking about one-dimensional motion, the coordinate system is pretty simple. What do you suppose it is? How could we describe motion along a line in the coordinate system? Sort of like a graph, but do we even really need a very complicated graph for that? Couldn't we just get by maybe with even something like that? Just like a number line, for example, right? We've talked about it in math as being a number line. Usually in math, if we talk about just one axis, we make it the x-axis. Not always, but typically, right? And so we can think about it as just being the x-axis, right? If we want to define some reference point on there, it can be any place, but usually we would assign 0 to be kind of our reference point. We're going to measure all of our motion relative along that line relative to that point. Okay? What if we're in 2 dimensions? Then it gets a little more complicated. Now what's our coordinate system going to look like? I think I heard it. Like it's like a graph, right? What do we usually call that? X X and Y axes, Cartesian coordinate system, something like that, right? So it's going to look like that. Okay. Where do we define our reference point there, you suppose? The origin, right? The 0 for both axes. Okay, and then finally, if we want to get even more sophisticated, we live in a three-dimensional universe, right? If we want to describe our motion in 3 dimensions, we're going to have to add even one more axis. We've got our x-axis, we've got our y-axis, and where does the third one go? Z-axis, and it's coming straight out of the board, right? So kind of like that. Agree? Okay. 3-dimensional motion looks really sophisticated, and it is a little more complicated, but not that much. We can understand most of the important aspects of motion by looking exclusively at 1-dimensional motion and 2-dimensional motion. And today, we're really just going to look at 1-dimensional motion. And that'll give you a pretty good operational definition of, or operational understanding, working understanding of the motion quantities that we're going to discuss today. Really, 1 dimension is enough for now. We might look at maybe 1 or 2 brief examples of 2 dimensions. There's one other part to this, though, that we need. We need to be able to orient ourselves in our space, whether it's 1-dimensional or 2-dimensional or 3-dimensional, via a coordinate system. But there's another part of this motion, too, that we have to take into account. If I want to explore my path from some point to some other point, I need to be able to describe where I started and where I ended on the coordinate system, right? But I probably also need something else. What? It is? I'll give you an example. Let's just say I'm constrained to walk in a line on the front of the room. So we'll make it real simple. 1-dimensional motion. If I start, let's say, right here, let's just say this is at 0, and I end out here at 5. Is that enough to describe all aspects of my motion? If I just know that I started at 0 and ended at 5 meters, let's say. What else might you want to know about my trip? The time. How long did it take me, right? There's a big difference between the situation where it takes me an hour to get from there to there, or if it takes me 2 seconds. That's going to look dramatically different, isn't it? Right, so we need a coordinate system, and we also need some way to record the elapsed time. Okay. So we also need to have some reference time. Now, typically the way we'll talk about that is with our imaginary stopwatch. We're going to start the stopwatch at the beginning of the event, whatever it is, right? And we'll stop it at the end. Does it have to be a stopwatch? No, it doesn't. It could just be that, for example, if we had a video recorder, if you were videotaping everything I'm doing up here, well, then at some point, most video recorders now, they're going to have some elapsed time that shows up somewhere in the camera, right? And you can make it show up if you wanted to. So maybe it's not at exactly 0, but if I'm going to start the trip right now, you could just look down in the corner and see the time that it shows on the video recorder, right? Let's just say hypothetically that when I start my trip, it's at 13 minutes and 1.3 seconds. If that's when I start, and then you notice that when you get to the frame where I'm right here, you look down at the bottom corner of the video recorder and it says 13 minutes, 3.3 seconds. How do I calculate my elapsed time? Just subtract them, right? So I have to have some reference time, call it that, right? And in order to calculate the elapsed time. Okay, getting the idea. All right. So let's look at a couple examples of this. Let's talk about position. We're going to start in just 1 dimension. 1 dimension, it's pretty simple. My position is just where I am relative to 0. Okay? Let's make 0 right here, and let's say that I'm starting at 1 meter to the left of 0. Okay, what's my position then, do you suppose? How would you describe that? I mean, you could say 1 meter to the left of 0, and that pretty much describes it. On a one-dimensional axis, if that's 0, what is the, I guess I didn't cover this. What is the understood positive direction? What's our convention for that? What do we always take to be positive on a number line?
Right.
To the right. Okay, good. So then if there's 0 and I'm standing 1 meter to the left, where am I actually standing on the number line? Negative 1 meter. Okay, so that's my position to start with. Okay, is that okay? Good enough. My final position. Let's say I walk out here and I end up at positive 2 meters. I said that wrong. I'm 2 meters to the right of 0. What's my position? Positive 2 meters. Okay. I want to talk about, if I'm talking about my motion from beginning to end, I really want to talk about the difference in those two values, don't I? Okay, so I could say that my initial position, in this case, equals negative 1 meters, and my final position equals positive 2 meters. Well, if I want to talk about how much my position changed, I call that quantity displacement. Can anybody tell me what my displacement was for that trip?
3 meters.
Positive 3. Good, because displacement is just going to be my final position minus initial position, right? Okay. If I said that my initial position was negative 13 meters, that means something to you, doesn't it? Where would I be? If this is 0, where would I be?
13.
I'd be, yeah, probably over in Mrs. Jones' room somewhere, right? That's cool. I have to go through the wall to get there, but I'm going to be over there someplace. Can I describe that place exclusively with a number? You might say yes, I guess, in a way, because the negative 13 does it, doesn't it? But that means that I know where the starting point is. Let's make this just a little more complicated. Okay, let's just say now, instead of limiting ourselves for just a moment to moving along a line, let's let ourselves float in 2 dimensions instead. We can move in 2 dimensions freely. So here's my reference point right there at the origin, right? If my initial position now is, let's say is it enough for me to say it's 7 meters? It's not quite enough, is it? If I just say my initial position is 7 meters from the origin, why is that a problem? Which way? It could be, really, that could be any place on a circle with a radius of 7 meters, couldn't it? Right? That's not specific enough. If I want to describe a position, I need to have a number, like 7 meters, but I also need what? I need a direction, right? So let's say that I'm going to be, well, I'm going to be right here. Now, that limits all the places on that circle to one place, the one place that's 7 meters away in that direction, okay? Then we know what we call that kind of a quantity that needs both a magnitude, so it needed a number, but it also needed a direction. That's a vector, yeah. Vector quantities are very important quantities in physics. They carry more information than other quantities that don't need a direction. A vector always has to have these 2 pieces. It always has to have a magnitude and a direction. It's only natural that our representation of a vector is an arrow, right? Because the length of the arrow determines the number part of it, right? That's what we call the magnitude, the length of the arrow, and the direction in which the arrow is pointing indicates the direction associated with that vector quantity. Okay, so let's say that I start right here. I'm going to call that then, that vector quantity, that is my initial position. Now the book uses the symbol D for position. I'm not sure exactly why. Usually books would use S. Almost every physics book I've ever used has used S. But that's okay. We'll call it D. I'm going to put the 0 there to indicate that it's the initial position. Why do you suppose we choose a 0? That's when I start my stopwatch, right? My imaginary stopwatch. I start it, and wherever I am when I start it, that's my initial position. So at time 0, that's our position. Now, it's a vector quantity, though. To indicate that this is a vector quantity, your book writes it in boldface type. I can't really do that. So I'm going to do the traditional thing, and I'm going to write it with a vector hat. Whenever you put this symbol over a quantity, that tells you that it's a vector quantity, and it needs both a magnitude and a direction. Okay? Let's say that we end up right here. Okay, so that's my final position. So relative to my reference point, that's my final position. So it needs a vector hat. I would probably just call that a D or a D sub F for D final. The notation in our book is they put a 1 there, which seems a little strange to me, but that's okay. We'll roll with it. It's fine. It'll work. So that means final position. What's my displacement then? What would my displacement look like?
D1 minus D.
Yeah, it's D1 minus D sub 0, right? Final position minus initial position. But that's kind of a complicated thing that we're not going to deal with until chapter 4. We don't really learn about the algebra of vectors until we get into chapter 4. And even then we don't learn an awful lot. We just learn what we need to kind of get by for now. But think of it this way. It's the change in my position vectors, and so would you agree that if I had to write that as a vector, it would look like this? Because I'm starting there and I'm ending there, right? So that's my displacement vector, and I'm going to write that as delta D. What does delta mean in physics? Change in, yeah. So we interpret that as change in position. Displacement is change in position. My final position minus my initial position. Okay? I'm going to play a trick on you now. Let's take the same situation, but I'm going to define a new coordinate system. Instead of this being my XY coordinate system, let's pick a different one. Let's pick, how about this one right here, where this is my new Y, call it Y prime, and this is my new X, call it X prime. So now what does my initial position vector look like? Very different, doesn't it? There's my new reference point, and there's my initial position, right? So the vector now would look maybe like that. It's a lot bigger initial position, isn't it? A lot bigger initial position vector, at least the magnitude is, right? So we'll call that D naught or D sub 0. When we say naught in physics, it just means sub 0. Okay? I'm going to call it prime, though, because it's in our new coordinate system. Where is our final position vector? Well, that's our reference point. Isn't it right there? Agreed? So that's D1 prime. What about our displacement vector? Has it changed? It's the same. How about that? That's important. The displacement vector is still the same vector. So the displacement is independent of the coordinate system that we choose, right? That's absolute. That's important. Okay. We'll come back to that again and again. Okay. So let's move back up to the front of the board. Okay, let's get a little more sophisticated here. We've got position. We know it's a vector quantity. Let's define another vector quantity that's very useful for us in our description of motion. if I want to, and you kind of have a sense of this already, if I start here and I end here, knowing my displacement alone is really not enough, right? You told me earlier that displacement needs to be combined with time in a way, doesn't it? The elapsed time tells me something important about the journey. Can you think of a quantity that mixes together displacement and time in a way that describes my motion? Speed. Okay, what about speed? That might work, huh? We know speed means something to us. If something is fast, if it has a large speed, right, then that means we know what that looks like. A bullet is fast. It has a lot of speed, but a turtle crawling along is very slow, right? It's not covering ground very rapidly at all, okay? The displacement. So speed is the word that we want to focus on. Almost. Almost. I'm going to tweak that word just a little bit. In physics, speed means something that's not exactly what we're looking for, and we'll get to it shortly. The word we're looking for is velocity. And I'll explain the difference here in just a second. Velocity, and I'm going to be a little more specific here. We're going to start off talking about average velocity. Velocity we'll get back to and explore in great detail, but the definition of average velocity, which we write this way. Whenever we talk about an average quantity, we put a bar over the top. Okay? So average velocity is equal to displacement divided by elapsed time. Okay? Displacement, did we agree on this? Would you agree with me that displacement is a vector quantity based on that picture? Because if we're starting here and ending here, the displacement definitely has a distinct direction to it, doesn't it? Right? So displacement is a vector quantity. Do you think velocity is a vector quantity based on this formula? What do you think? Velocity is displacement divided by elapsed time. And when I say delta t, do you understand what that means? Delta t really is just my final time minus my initial time. If we're using our imaginary stopwatch, my initial time I can always let just that be 0. How about it, right? Okay. You think it's vector? Maybe, but let's explore it and see. So how about if we take an example along the front of the board up here. Let's calculate my velocity as I move in one dimension. Let's say I'm going to start off, so how about if we make the plug-in here, that's going to be 0. So I'm going to start off at 0, and I'm going to walk out 2 meters in 1 second. Let's calculate my velocity. Okay. What's my displacement? 2 meters, right? Starting at 0 and ending at 2. Agreed? So I'm going to get 2 meters minus 0 meters divided by 1 second equals what? 2, and my units would just be meters per second. Okay. Okay, good. So still maybe indeterminate. That's maybe it's not a vector. Let's try another one. Let's say I start at 2 and I end up at 0, and it takes me 1 second to get there. Now what's my displacement? -2. Let's look at that. In this case, we're going to get my ending position, my final position is 0. My starting position is 2 meters, and it's always final minus initial, isn't it? Right? Final position minus initial position is my displacement, my change in position. So I get an answer of -2 meters per second. Now, answer that question again. Do you suppose velocity is a vector quantity? Yeah, it has to be, doesn't it? Because I got different answers for essentially the same trip, only just reversing the direction, right? Changing the direction changed my answer from positive to negative. If I adopt the convention that to the right is positive. Make sense? Okay? Agreed? How about this one? What's my average velocity if I start at, let's say, -1, and here's my trip. I'm going to go clear out to +3 and back to +1, and it's going to take me a total of 2 seconds to do that. Start at -1, clear out to +3, and then back off to +1. What's my average velocity? Ooh, there's a couple different answers that make sense, don't they? Somebody, tell me one answer that might make sense. I don't care if it's right or wrong. What?
1/2.
1/2. How'd you get that?
Because where you ended, you started at 0 and went to 1.
Okay, actually I started at -1.
Oh,
So then what are you gonna say?
I'm gonna say
1. Okay, now you're saying because I end up at +1, I started at -1, and it took me 2 seconds.
Yeah.
That's a reasonable answer. Anybody else have another potentially reasonable answer here?
3, because you went from -1 to 3, which is 4,
Mm-hmm.
and then back to 2, you said?
Right,
Which is another 2, which is
Okay.
6,
okay.
over the 2 seconds.
So you could also maybe, has everybody seen an argument for 3 meters per second also being a good solution there? Okay, which one is it? If we have to vote, let's vote. And I'll tell you what it is, but I'm just curious, what do you think? Is it 1 or is it 3? How many people say 1? How many people say 3? Oh, it's pretty even, I think maybe more lean to 1. Okay, the answer is 1. And here's why. Because it's a vector quantity. Because all it depends on is my final position and my initial position. Okay, so if we strictly apply this formula, our average velocity in this case is +1 meter minus -1 meter over 2 seconds. Well, 1 plus -1 is 2, right? So I get 2 over 2, which is 1 meter per second, +1. Here's a way to think about that. The average velocity is just the easiest story we could tell that has the same outcome. That was kind of a complicated story. If I start at -1 and go clear out here and back to 1, couldn't I have the same ending if I just start at -1 and I just move along at 1 meter per second for 2 seconds and end up right here at the very same spot? Make sense? Okay, that's all the average velocity cares about, is where I end up and where I start. What if I did this? What if I start at 0 and I go out 10 meters and come back 10 meters in 4 seconds? What's my average velocity? 0. How come? Ended up right where I started, right? Is that a little bit unsatisfying though? I mean, because that's different. If I just stand here for 4 seconds, that's very different than going out 10 meters and coming back 10 meters. So there must be some other way to describe this that takes that path into account. It's just not average velocity. What do you think it is? Well, kind of. I mean, not really. We'll get to that in a second. What's the other word that we throw around to describe my motion from one instant to the next? If we want to describe sort of the flavor of my motion. We talked about average velocity, but that's not the first word that was thrown out. It was speed. Speed is different. Speed is not a vector quantity. All speed cares about is the number quantity of how much distance did I travel in how much time. So I get a different answer for speed. If I start here and I go out 10 meters and I come back 10 meters, what's the total distance I've traveled? 20. Distance can never be negative. Distance is an only positive kind of quantity. It wants to know how much elapsed distance, how far did I walk, for example, or run, or whatever I was doing. 20 meters. And how long? 4 seconds. So what's my average speed? 5. Okay, that's a different answer, right? You get that? So we've got average velocity is displacement over time. Compare that to average speed is just, we'll call it S, and actually we won't even call it S. We're going to call it D, but without the vector hat. So it's like the non-vector version of displacement. Of velocity. So it's V without the vector hat. And it's equal to distance over time. Okay, total distance over time. Right? Make sense? Okay. Can speed and velocity be the same thing? Sure. I'm traveling in one direction, right? But typically they're not. If you're driving around in a car, what is what precisely describes that instrument that you look at when you're driving along the road? It's a speedometer then, it's not a velocitometer, is it? All we really care about is how much distance are we covering over time. If it were a velocitometer, I could travel to Portland and back in, well, I don't know, if I was going really fast, maybe like 4 hours, right? And my velocitometer would have read 0, but obviously I burned a lot of gas doing that, right? So that's definitely a speedometer. If it were a velocitometer, it'd be kind of hard to read. If I was driving along the road, a straight section of road going north, it might say something like 65 miles per hour north. Okay, that's helpful. That tells me something. But as I turn my car, now it might start to say 35 miles per hour north, 25 miles per hour west. Well, that's not as helpful, is it? That doesn't tell me, am I going to get a ticket or not? I just want to know what my speed is, right? Okay. All right, questions so far? That making sense? All right, so how about acceleration then? Let's move on to the last of our quantities I'm going to introduce today. Acceleration. I'm going to talk about average acceleration. Okay, average acceleration is, anybody want to take a stab at it? What do you think? And I'll give you a hint. It is a vector quantity. What do you think acceleration is? Okay, good. So it's going to be change. I'm going to write it as an A. Got to put that in there. So average acceleration, I need to make that a bar, okay, is equal to change in velocity over change in time. Change in time, right? Okay. So that's acceleration. Okay, so now let's go back and let's go to our one-dimensional situation and let's talk acceleration instead. Let's say that I'm walking in this direction when we start our stopwatch. We start our stopwatch, I'm at -1 meters. Okay, I'm walking along and I'm walking at constant speed and I end up right here. Okay, at +2 meters. What's my acceleration? Kind of a trick question. What is it? It's a trick question. I gave you a lot of extraneous information here. I'll do it again.
We don't have time.
That's right. Okay, I'll tell you time. So I start the stopwatch right here. I'm at -1 meters, and I'm walking along in this direction at constant speed. And I end up right here at +2 meters after 3 seconds. What's my acceleration? What is it? Say it again. How'd you get that?
You said constant.
I said constant speed. So if I'm moving in the same direction at constant speed, doesn't that mean that my velocity is constant also? Right? I'm always walking in that direction at the same speed, right? Speed is really like the magnitude of velocity in this case, isn't it? Right? So I don't even know what my speed, I guess I know what my speed was. If it took me, what was it? 3 seconds to go 3 meters, right? So what's my speed?
1 meter per second.
So meter per second, 3 meters over 3 seconds. Positives, I'm going in that direction. Did it ever change though? No. So my acceleration then by definition is going to be 3 meters per second minus 3 meters per second over 3 seconds, right? My final speed minus my starting speed, they're the same thing, right? So I end up with 0, and the units are going to be weird, aren't they? I'm going to get 0 meters per second. Yikes. Here's what we do with that in physics. We write that as, if I have a fraction over a fraction, I just flip and multiply, don't I? So I would multiply meters per second by 1 over seconds, and I get 0 meters per second squared. That's our standard unit for acceleration. But I got none of it there, and that makes sense. Acceleration is the only kinematic quantity that we've talked about so far that you can actually feel. You can't feel position. If I stand here and close my eyes, that doesn't feel any different than, I'll try it. No difference. It's the same. It's the same. if I'm driving along in my car and the cruise control is on and I'm taking a nap, can I tell, I mean, as far as I'm concerned, I might just be idling on the side of the road, right? I can't tell any difference. Agreed? You've all had that experience. But if you're riding in the car and somebody steps on the gas and you start to change your speed, you can feel that, can't you? That feels like something. So acceleration is the only one that we can actually feel independently, even with our eyes closed, right? So we know, in this case, there was no acceleration though, right? I wouldn't have noticed any difference. I could have been cruising along in cruise control in my car, right? But now let's change it. Let's say that I'm going to start here at rest, okay? And I'm going to change my speed at a constant rate. And after 2 seconds, I'm going to be cruising along at 5 meters per second. Now let's calculate my acceleration. What is it? My average acceleration would be what? What's my final velocity, did we say? 5 meters per second, right? Positive 5 meters per second. Minus my initial velocity. I was at rest, so it's 0, right? Divided by 2 seconds, I think I said. Equals what? Yeah, 5 divided by 2 is, if we want to make it a decimal, 2.5. And my units would be meters per second or meters per second squared. Positive. Okay. Now let's do this. Oh gosh. Last example I want to get through. Now let's say I'm cruising along at 5 meters per second when I start the stopwatch, and I'm coming to a rest. After 2 seconds, I screech to a halt. Now what's my acceleration in that case? So my average acceleration is going to be, my final velocity is 0 minus my initial velocity of 5 divided by 2 seconds. Well, that's negative 2.5. Why is it negative? Okay, because I changed my stuff. I changed my velocity. Okay, hold that thought. That's what we'll pick up tomorrow. Is that making sense?
Yeah.
Okay.